Morning. I would like to first thank Dr. Muhammad and his team for putting together this conference. I'd also like to thank the team that who worked towards the end of this presentation. We'll be sharing some of our Joint Center of Excellence work. So I'll be talking about AI for material innovation. I will not dive deep into any details. I'll try to make it more on. It was like more on a survey covering AI, like serving materials, and some of the key applications we're focused on. Uh, so as many of you know, so there are different types of materials: metals, ceramics, polymers, composites, and MOFs. And for us, we're focused on MOFs mainly. The AI challenges facing materials is data scarcity, complex structure, property relationships, and resource-intensive discovery. So we need to find ways to help us to still be able to serve material science, which I'll go in shortly, and overcome some of these challenges as much as we can. Metal organic framework materials help us tackle different problems as they are advanced materials having special properties and dynamics. They could be used in gas storage, drug synthesis and delivery, in electronics, in carbon capture and CO2, in HVAC, and water harvesting. Carbon capture and water harvesting are two of the main applications we are focused on. And this serves the Sustainable Development Goals. We can use AI to better enhance the quality of materials, to better have a sustainable polymers that can help in the sustainable polymers and carbon capture using MOFs. And how we can utilize AI for material innovation. So we can have, for example, predictive modeling. We can have as well ways to discover properties, to do simulation. There are ways to learn relationships. In the discovery and screening, it will help us to screen vast material databases and for different potential candidates of interest. And lastly, synthesizing optimization, as this is a very challenging problem. And recently, with generative AI models becoming accessible, this could be used for synthesizing and minimizing the traditional approaches and trial and error. I'm not going to go deep into the Go Fair initiative, but since I mentioned the challenges that we go through, many of the challenges I've mentioned can be solved and tackled if the research community adopted the Go Fair initiative. So it helps having the data more accessible, findable, interoperable, and reusable, meaning if we need to find certain information, we're able to find the data and we can access it, we can get it, and we can have it work with different with our models easily. And at the same time, reusable. So the data that we have can be reused within the research ecosystem. These are state of the art examples made by I would say leading entities, Microsoft, and the second slide will be for Google. So Microsoft Research AI for Science, for example, have developed MatterGen to use generative AI to design stable and diverse inorganic material, while MatterSim is a deep learning model that helps in having material simulation and property prediction. For Google DeepMind, they have a number of contributions. They're also working with the Berkeley lab. They have synthesized or discovered over, I would say, I think 2 million, over 2 million crystals, and over 300,000 were considered stable. If you're interested in these works, they're all available online to read. And then there is also the state of the last example in my presentation for the state of the art, I would say, this is a tool more. So they provide software, a supercomputer, and screening under the materials project, led by Berkeley, but it has multi-institutions and it's a multinational project in its nature. They have many publications covering the contributions they've done in each one of their services, and how they work together with the ecosystem. This is an interesting example. It is a project that was conducted in KAXT a few years ago. It's not in the chemistry perspective, but more on the physics side. So how to use machine learning to improve aerodynamics and improve the wing design for an aircraft. This was an approach for a material scientist with a background in physics, solving an aerodynamics problem. Also, these papers are available online, and they try to improve the airfoil and optimize the aerodynamics using Gaussian processes and neural network-based surrogate models. And then we have here the development of data-driven machine learning models for the prediction and design of permadyne corrosion inhibitors, using machine learning here to overcome common challenges, like trying to see how to tackle corrosion, and this is where machine learning helps us explore many things with ease. I would go with our team. So our team. This is the Joint Center of Excellence for Nanomaterials and the Clean Energy Applications under KAXT, and jointly with the University of Berkeley, with Professor Omar Yagi on the Berkeley side, and Dr. Majid Al-Awad on the KAXT side, leading this center. I would like to thank everyone who has contributed to the work I've either shared or preparing the presentation. As well as so the research group, sorry, the Joint Center of Excellence is focused on the integration of artificial intelligence, utilizing AI for predicting new frameworks for MOPS. Also, water harvesting from air. We have also the CO2 capture and conversion, which is of high interest in our Joint Center of Excellence. Then there is the recent achievements we had. These are two papers. One was in Nature. The other one was for using ChatGPT, which my colleague Hanan will share with you. Thank you.
Thank you very much, Dr. Arwa Alabdulkarim, and your insightful presentation and sharing these groundbreaking activities that's being done is truly basically symbolize the intersection between AI and also chemistry. So now we are really excited to continue our session to our next speakers before we open the floor to questions. So welcome, Dr. Hanan.
Okay, sorry. I think I have to repeat what I said. So, you can hear me now?
Yes.
Yes, okay. So I said thank you, Dr. Muhammad and Arwa. And the next half of our talk about large language model in chemical sciences. I am Hanan Almurayshed, a researcher in AI and Robotics Institute at CAXT, and my research focus in machine learning and natural language processing, which represent the umbrella of large language model. So I will take you on journey on literature about how LLM used in chemical sciences from data to discovery. So it's like a technical perspective about those work. But before that, we talk a little bit about a large language model. So the large language model evolved significantly from a traditional neural network until Google introduced a transformer architecture that enabled the powerful text generation and understanding capabilities. And then those models grow up and scaling up, especially with the increasing of computational power and the existing of larger training data set. And those things lead to exponential growth in LLM capabilities. One of those recent capabilities, it's the multimodality. So LLM now can process and generate different kind of input like text, images, video, and those expanding their application in different area. One of them is a chemical science or chemistry. Here, this timeline represents the rapid rise of large language model, and this is specific for a chemistry. And this timeline started on 2017 when Google introduced transform architecture, and then we have BERT model, T5, BART, and recently GPT. Though all of those models share the same architecture, which is a transformer, but they differ in the way of training and the number of trainable parameters. So the question here, what can LLM do for chemical sciences? So what's the application areas? We can say it could fall into four main categories. The first thing, data mining and curation, because LLMs have a capability on understanding and generating text, so or generating different kind of input, so can rapidly extract key insight from a scientific literature, all that enable an efficient data mining and curation on a chemical discovery. Also, we have a workflow automation, like especially in the lab. So by automating a routine task, summarization, experimental planning, streamline chemical research workflow. Also, we have some application specific on a molecule design. So could predict molecular properties and reactions. Also, that lead to a design of a new chemical compounds and materials with a desired characteristic. So all of those applications can combine to accelerate the chemical discovery. So LLM can connect areas of chemistry, fostering interdisciplinary and collaboration to accelerate the scientific discovery. So I will share some example about those applications, but before that, I want to answer this question: how are LLMs adapted from a technical way? We can call this application level. So we can say there are three different level of adaptation. The first one is standard LLM. That means we just prompt the already existing pre-trained general purpose LLM like GPT models from OpenAI by just prompt those without any kind of customization. Also, we have another level of adaptation by fine-tuned or using a recent technique called in-context learning. So that means we have a pre-trained model, but we adapted on a specific domain using chemistry-specific dataset. So fine-tuning, that means we train LLM further on a specialized dataset to adapt this model on a specific task or domain. Also, we have another kind of learning called in-context learning. So we just provide some examples. We call it chat with the prompt to let the LLM know how the answer could be. Also, we have the most advanced level of adaptation. We can call it custom built LLMs. So that means we build LLMs from a scratch. We talk about advanced topic like representation, tokenization, pre-training, post-training, and also the architecture of this model, and etc. So this is the first work in literature related to the data mining applications. So this work from Prof. Maryagi's group in University of Berkeley, and this work published, reviewed and published in Journal of Digital Discovery from Royal Society of Chemistry, and their work about utilizing GPT-4V and use it to so GPT-4V, it's a LLM with a vision capability, so it can understand images and give some insight about it. So they use GPT-4V to treat the literature as an image and ask them to analyze the provided literature paper page as an image to determine if it include 5 classes of experimental plots. So the GPT-4V recognize and identify the plots on this page, and then make like a checklist regarding those classes. So it's like an automate the labor-intensive process of recognizing, categorizing, and interpreting experimental plot in scientific literature. So in here, the confusion matrix, so they evaluate those output and they compare the predicted choice from GPT-4V with the actual choices done by human, and mostly GPT-4V work well on this kind of task. Here we have a recent work from our joint center between KAXT and Berkeley under Prof. Maryagi's and Dr. Majid Al-Awad. And this work about using a GPT-4V to create a dataset, a single and multi-hub question answering dataset for reticular chemistry. And this generated dataset or curated dataset, it contains 3 different kind of questions: factual, reasoning, and true and false. Factual, that means the question for which the answer is a stated fact. Reasoning, that means to answer this question, LLM need or the model need to some kind of understanding to answer this question. And the true and false, that means question for the answer is either true or false. Also, we have 2 different kind of a process of answering those questions. So here we have a single hub and multi-hub. Single hub, that means the answer need only 1 chunk of text to answer this question, and multi-hub, that means the LLM need more than 1 chunk or place of text to answer this question. And here, this is some highlighted result from this work. So this dataset generated or curated using 2.5K research papers. Also, they utilized OpenAI GPT-4 Turbo, and the question type includes single hub and multi-hub question answering. Every type include around 45K question answering pairs. So that means we have as a total around 90K question answer pairs. So this kind of work, it helped a lot on the era of large language models. So we can use it for a fine-tune model or train a large language model using those data. Another work here, we still in the area of data mining and curation, but here we go to the next one, which is automate workflow automation. So here this work utilized GPT-4 to connect the literature with the practice. So they convert a literature experimental procedure into actionable step. So they ask GPT-4 to extract a detailed protocol from the literature, and then ask the prompt again, ask the GPT-4 again to write those protocol as a machine readable XML, and then send it to automated lab reactor. So they bridging the gap between the textual procedure and automated laboratory work. Here we will go further in the adaptation level. So here TX LLM, it's a work from Google research team and Google DeepMind teams. So they fine-tune a Balum model. It's a pre-trained large language model with data related to the therapeutics. So before the fine-tuning, they create their data set, which include different topics related to the drug discovery and therapeutics, and then they create their data, and it's about a 66 tasks related to those topics. and contain around 700 data set. As a result, they have here around 10 million question answering pairs used to fine-tune the BALM model. Those pairs fall under three different categories of task as a classification. So the answer, it's a multiple choice, and here the generation, that means the answer it would be a textual in a textual way. For the regression, that means the answer is a continuous number or a numerical in general. So they use those data, and this data represent the domain from early stage of target identification and validation till the clinical trial. So they trained or fine-tuned the model, which call it TX LLM. And this kind of model or fine-tuned model that have a specific domain help a lot to reduce the time and reduce the cost, as they reported in the paper. Here another type of learning, which is in context learning. So here they target the molecule caption translation. That means they give the LLM a molecule and ask about the caption, or give the caption and then ask about molecule. So the idea of in context learning, it's about provide some example with the prompt to let the LLM know how the answer would be. So here they have a retriever to retrieve a similar input, the similar examples from a database that similar to this input, and then pick the top end example and include it in the prompt. So the prompt include rule identification, task description, with output and instruction, and then they send this prompt to LLM, and here they use ChatGPT as example. And then after they take the response from ChatGPT, they do some validation step to doing the desired output. Here, for the most advanced level of application that build everything from scratch, here a drug LLM, it's open large language model for a molecule generation. So they tolerate the idea of LLM. So they do everything from scratch by introduce a group-based molecular representation to encode a molecule into a sequential way called GMR, and then use the sequential data to train the transformer or a drug LLM. And then, so also they adapt the idea of a training. So the general purpose LLM, they train by try to predict the next token based on the previous context. But here, they train the drug LLM to predict the next molecule based on the past modification. So this kind of customization demonstrates a strong future learning capability to generate new molecules with desired properties, as they mentioned in on their work. So this just a quick journey. We start from a simple thing by just prompting the GPT or ChatGPT for data mining and data curation till we discuss the most advanced level of customization by creating a new algorithm to build a LLM for a specific area like a molecule generation. So that's it. Thank you for listening.
Thank you very much, all. And I think we can keep the floor to the questions.
Yeah.
Okay, I see several questions in the Q&A from Miriam. So she was asking which development environment that's basically being used to process these tasks. So I don't know if you can answer this question.
Okay, about any presentation for me or for Arwa?
I think it's for you, given that it's at 10:32.
So I didn't understand what she meant about development environment for which work.
So they mentioned several examples like Google AI Studio, Google Colab, Jupyter Notebook, or just like Python.
If she meant the work of generating a reticular chemistry dataset, we used the ChatGPT or OpenAI API. It's not one of those apps or environment.
Yeah, thank you very much. I think we have another question also, just like about the accuracy of the results. What are the best ways that we can improve the accuracy of these models from your perspective?
So to customize the LLM to a specific kind of area, I think fine-tuning or using the in-context and its most suitable technique to make sure that the model work for the desired domain.
Yeah, I think we will take one more questions by Dr. Sheikh Alardi. So she was asking, how did you convert the molecules to GMR?
So this is not this work not under a text. So I just mentioned this work as an example about the application of customization. So they provide an algorithm to encode this kind of representation.
Thank you very much, Dr. Hanan, as well as Dr. Arwa, for basically your enlightening presentation on the advancements in AI and machine learning, and it's basically correlation to chemistry. And I believe that these insights have really benefited a lot the participants. So we appreciate your contributions to the field and your participation today. So now, given that our next speaker will be basically starting at 11 a.m., so you may write your questions in the Q&A, and hopefully that the speakers can basically answer some of them. And we will be waiting until 11 a.m. KSA time until we introduce our next speaker, which will be Dr. Hussein Joya. He's the chemistry manager at MathWorks, and we will be delighted to have him by 11 a.m. So until that time, we will have a break of 20 minutes until the next speaker. So thank you all.